Why are systems of differential equations interesting? First of all, many applications can be seen as a system of differential equations. As a first example, we will see that this holds for a mass spring system. And secondly, we can convert higher order equations to a system of differential equations. These systems are easier to analyze than the original higher order equations. And thirdly, when solving differential equations numerically, you have to convert them to a system of differential equations in order to use standard solvers in packages. So, enough reasons to look into these systems. But how do we do this conversion? Fortunately, that's easy, as you will see in this video. First we look into the application, so our famous mass spring system. Mass times acceleration plus friction times velocity plus spring constant times displacement equals some f of t, some force. So this is a second order differential equation. However, we can convert this to a system of differential equations and we use the following strategy. As our x1 we choose x and then we choose as our x2, our second dependent variable, x prime. So why do we do this? Well, if we do it like this, we can compute x1 prime equals x prime and x prime equals x2. So our first equation becomes x1 prime equals x2. And then for the second equation, x2 prime equals x double prime. But x double prime, we know what that is. We can solve for it using our differential equation over here. M times x double prime equals f minus cx prime minus kx. So if we want x double prime, we have to divide by m, and there it is. Now it's still expressed in terms of x prime and x. However, we can get rid of those, of course. x2 prime equals then f of t over m minus c over m times x prime, but x prime equals x2, so there it is. Minus k over prime times x, but x equals x1, so there it is. So then we have our system of differential equations. x1 prime equals x2 and x2 prime equals f over m times something minus something depending on x2 minus something depending on x1. So there we are. So now we have converted our mass spring system, our second order equation, into a system of first order differential equations. Now, how can we do this in a bit larger example? And we can use the same trick, say in this example 1. So we have the fourth derivative now of u with respect to time minus 3 times u equals 0. So how do we convert this into a system? Well, we choose the following, set again now u equals x1, u prime equals x2, but now we have to go on. We put u double equals x3 and u triple equals x4. So how does our system of differential equations look like now? Now x1 prime equals u prime and u prime equals x2. Then x2 prime equals u double and u double equals x3. x3 prime equals u triple, because we differentiate that one, and u triple equals x4. So those are our first equations, x1 prime, x2 prime, x3 prime. And then x4 prime equals u4, but u4 equals 3 times u equals 3 times x1. So what do we get as our system? x1 prime equals x2, x2 prime equals x3, x3 prime equals x4, and x4 prime equals 3 times x1. So using this strategy, we can always easily convert a larger order differential equation into a system of first order differential equations.